going to change the input resistance and see the effect of the motor. So you've got two graphs running in parallel. When you call it up the first time, it'll probably be in pause mode. It needs to be in run mode. You'll see that the speed is proportional up to a point. Whatever I do now, it doesn't get any faster. Remind yourself of what I said earlier about a transistor conducting as much as it can. What do we call it? Saturated? Whatever I do now, beyond that point, it won't go any faster. Or only marginally faster. It is now saturated. Small changes there are making no difference. Large changes later. At any point, prove that the gain of that transistor, the first one of our Darlington pair, is 200. The second one is switching the current, 40. That multiplied by that is the same as that multiplied by that, 8,000. Let me run it to almost saturation. 0.04 multiplied by 124 is several hundred gain. So at various points, just do the sums to work out the gain. Now that's easy peasy. What's happening is it's reacting quickly. If you want a bit of fun, this is the extension activity for the more able. Try this one. That's the answer. Don't want the answer. I've changed the motor now for one with a flywheel on it. A large mass. When I run this one, run down here, there we are. Because there's a flywheel on there, it's still running. The energy is stored in the flywheel. The motor is slowly slowing down. You can change the mass of the flywheel. Now if I turn that off totally, notice flywheel still running. All those figures are showing the reverse current. There is no power to that circuit. The power is coming from the flywheel itself. If that was a bandsaw, that would be dangerous, wouldn't it? Because the blade would still be running. Yeah? Have you noticed that when you turn a lot of electrical devices off with a motor, they instantly stop? That's because somebody has put a switch there. A push switch, which is connected to the on-off switch to take the back voltage back through the motor itself. So the current from the motor is being used itself to stop it. Now you're not going to build that bit next week, but you are going to build the variable resistor, two transistors. You won't stick meters in it. We'll put a diode in to protect the motor from destroying the transistor. We'll put a current limit resistor to make sure that on full load, and I can demonstrate that beautifully without blowing everything up. Let me restart the graphs. And rerun. Is that paused or running? That's now paused, running. When I remove the power, it's still continuing. There's the back EMF. If I take the current back through the motor itself, the resistance doesn't change because I've still got 10k resistance, but the effect of the brake was to decelerate quickly. So designers also use the current from devices to control the system itself. Now there's a lot for you to play with there. The session next Monday or Tuesday will be breadboarding that circuit, so you've got experience of handling it. The write-up will be quite simple. It'll be getting a graph from that, and it'll be explaining some of the points I've made for yourself as to why every component in that circuit is there. Not how it works, but why it's there. So let me go back one step to that one. We are making a breadboard model of an electrically powered device. Could be an electric drill, could be a hairdryer, could be a razor, kind of things you've been using with Howard. Curling tongs don't have motors in, so it's not one of those. Portable screwdriver, scale electric control for cars, train controller, where you can change the speed of the train. It's something which is used to control the speed of a motor. 2 transistors. The first one is high gain to switch the second one, which is low gain. Why do we need the second transistor? Because that one itself cannot handle the current. The second one can. We have a diode in it so that any back voltage is damped, is got rid of. We have a resistor to limit the current. Try yourself from the properties, the scene properties, to turn off the indestructible components. Try running it, try taking components out to blow the transistors up. Try it for yourself. Show that when the motor runs, that it still continues afterwards. That arrangement there, I shall focus on next week, is a potential divider from your first session. When that's 10k, the voltage is halfway there. So when I switch that on, 4.5 volts, the voltage there is about 2 volts. Your laptop responds very slowly. Yeah, very slowly. There's a time lag in it. So that's the halfway point. That's limit the current into the transistor. The base current has to be limited. I will ask you on the second transistor to put your fingers on it, because at full load no power, no load no power, but half load some current, some voltage. You should feel it getting warm. Think about what that's got to do with designing a handheld device. Do you want the handle to get hot? Where would you put the components? So when you built it next week, they're all the things we're going to consider. But I would like you to have a play around with the simulations yourself, especially the motor control one. And if you feel ambitious, try the one with the flywheel on it, to get the idea of the fact that the energy is still in the flywheel. Now I've skipped that fairly quickly. I've tried to keep the maths out of it. I know there are maths on the pages for the first page. Any calculation I put in a test will be basic, simple numbers. There will be never anything complicated. turn back to the front page before we go. I'm going to power that down. Make sure you are aware of the 3 transistor leads, their names. What we mean